Well, going back to the Boussinesq problem, the vertical stress at a point of interest is 3 times the intensity of the load, the depth of the point to the power of 3, and then 2 times pi times capital R to the power of 5, to the 5th power. And what is unique about this equation, or this expression, is that the material properties are missing. That means that the vertical stress in the half space due to the load P is not a function of the material properties. So it would be the same vertical stress regardless of the value of the elastic modulus, whether we are dealing with a very low modulus or very high modulus, and also not a function of the Poisson's ratio. This made the engineers think that this expression can be used regardless of any site understanding or any testing of material properties. This is of course 100% true if the assumptions of the half space are obeyed. That means that the half space is really elastic and isotropic and homogeneous. Let's look at the distribution of vertical stresses directly under the point force. So we have the point force, and we are looking for how sigma zz changes directly under the load. So that means as we change z. So in order to calculate this, we just insert r equal 0 to the above expression, and we end up with sigma zz for the special case of r equals 0 to be 3 times p divided by 2 pi, and then 1 over z squared. So basically what we learn is, if we were to plot sigma zz as a function of z, we learn that the stress is reduced in a proportional to the depth squared, or 1 over depth squared. And we can also see that if we approach the surface, which means that z is becoming smaller and smaller, getting closer to 0, the stresses explode and we have infinity. So there is a singular outcome for the surface, and that makes sense because the stress level directly below the point force is infinite. A point force is a force that is applied over an area that is 0, and that means that the stress is infinite. So actually the behavior of the vertical stress with depth is consistent with the assumption of a point force. So this chart here is for r equals 0. Additional expressions that are of interest: vertical displacement, that is uz, that's the movement of a point in the z direction, and this expression is also coming from Boussinesq, that is uz is p, capital P, 1 plus Poisson's ratio divided by 2 times pi times e times capital R, and then we have in parentheses 2 times 1 minus Poisson's ratio, and then z squared divided by r squared. Here we have a function. So the vertical displacement is a function of the material properties. It is inversely proportional to E. So for the same exact conditions, if E is doubled, then the vertical displacement is halved. This is unlike the vertical stress situation. Now, the vertical displacement on the surface of the half space is of practical importance. This is something I will show later, but what I mean by that is if we have the load applied here, the vertical displacement at the surface is how much a point that is some distance away from the applied load, how much this point deflects or is displaced downward. So of course, the further away the point is, the less it is displaced. And to calculate this specific case is done simply by inserting z equals 0 into the above expression, and we end up with uz for z equals 0 to be p, the intensity of the magnitude of the force, 2 times Poisson's ratio squared divided by pi, and then Young's modulus, and then this is multiplied by 1 over r. So what we can see here is that the surface displacement downward is decaying which is in a way that is proportional to 1 over the radial distance from the point of force application. If I were to plot this displacement, it would look like so, and this is proportional to 1 over r, where r is the radial distance from the point of force application to the point of evaluation. And as before, we have a singularity here. As r approaches 0, that means that we're just below the load. We get infinite value of displacement, which is what we can get from Boussinesq's solution. There's a singularity just below the load. You can find all other responses. For example, the value of shear, tau rz. We can find the value of stress in the radial direction, and we can also find the value of stress in the theta direction. So yes, there are no displacements in the theta direction, but there are stresses in the theta direction. And I suggest you look up these solutions, look up the book, which is an ebook available as a PDF, Elastic Solutions for Soil and Rock by H.G. Paulus and E.H. Davis. And there's a chapter about half-space solutions, and you can find the missing expressions for the other responses.